Which of the following partial sums is the first, which is at most 0.01 away from the value of, and then we have this sum, n equals 1 to infinity, negative 1 to the n plus 1 over n squared. Notice you have that negative 1 to a power. This is an alternating sum. And it goes to 0, so it converges. So we want to know how far do you have to go in the partial sum so you're at most 0.01 away, according to the error bound for alternating series. So using the error bound, which one of these sums is the right sum to look at? So essentially, we're going up and stopping at either 6, 7, 8, 9, or 10. Do we have an answer? What? I've heard D, I've heard E. Now remember, it has to be the first according to the alternating series. So is it D or E? It's D. Because when we're talking about error bound for alternating series, the error is the next number that you would add. And so you say, well, I want the next thing to be at most 0.01. Well, okay, so the next thing looks like 1 over n plus 1 squared. And you say, well, when does 1 over n plus 1 squared be less than or equal to 0.01? That's 1 over 100. So you end up with n equals 9. So you should stop at 9. All right, so remember it's the next term that drives the error, not the last term. It's not this term, the last term, it's the next term that tells you your error. Now, before we leave this problem, there's this command or instruction here on the end. According to the error bound for alternating series, if we drop that part, would the answer change? I mean, it's a philosophical question in some sense. So if we drop the instruction according to the error bound for alternating series and just asked, what's the first partial sum, which is at most 0.01 away from the true answer? Is it still D? I'm not expecting you to know. I'm just wondering what you think. The answer is B. B is the first partial sum that's at most 0.01 away. Now, I'm bringing this up just to remind you that when we talk about error bounds, we're never after, the best possible. Because to be able to do the best possible, you pretty much have to know the exact value, which is hopeless. When we talk about error bounds, we're saying, look, we just need to get something to control behavior. We're not always going to necessarily get the absolute best thing. We don't need the best. We just need to be good enough. That's all we need, just to be good enough. All right. Well, our thought for the day, courtesy of Charles Dodgson. She generally gave herself very good advice, though she very seldom followed it. Now, I think that this applies to a lot of people. I know it applies to me. You know what you need to do. I think there are people in this room who could give excellent presentations about what it takes to be a good student. But they don't follow it all the time. You know what you need to do. It's just a matter of doing it. Now, Charles Dodgson, you might wonder who is that. He was a mathematician, but he did other things as well. He wrote some books under a different name. Does anybody know another name he's known by? Lewis Carroll. Who do you think the she is? Given that it's Lewis Carroll. Alice. Alice from Alice in Wonderland. So, all right. Good. Now, I don't have a goal for today because today's a review day. So we're just going to be mainly reviewing, talking about things. So we have here's our big block. It's on the handout. This is, when it comes to convergence, this is what we need to know. There's a bunch of tests, and then there's some other basic facts. Now, we've talked about these tests many times, and we'll continue to talk about this test today. You have the nth term test. If the terms don't go to 0, you're done. Game's over. You diverge. Don't even have to do anything else. If the terms go to 0 and you're alternating, look for something that has a plus-minus thing going on. Sometimes it's plus minus 1 to the n. Sometimes it's cosine pi n. But if you see it alternating and going to 0, you're done. Converges. Well, maybe you're done. So sometimes they'll say, well, wait, it converges, but what kind of convergence? Because there's sort of two flavors. There's absolutely converging, which is very strong. It's the kind we like. And then there's conditionally convergent, which says you really need that plus minus. In other words, you need to have some cancellation going on in order for things to converge. So absolute convergence just means the sum of the absolute value converges. And if the sum of the absolute value converges, then the sum without the absolute value converges. Conditional means the sum by itself converges, but remove the signs, it diverges. So you might be asked to say, here's a series. Does it converge conditionally or absolutely? So you need to be able to say, I can tell you why it converges this way versus that way. Basically, get rid of the sign and do a convergence test. There's the integral test, which is very narrowly used. It's mainly used to help us get to p-series. But essentially it says the integral will converge if and only if the sum converges, as long as you have a function that's decreasing. We have our comparison test. We can try to get two series coming out of a pair of sequences. If the small sequence diverges, the big sequence diverges. If the big sequence converges, the small sequence converges. There's the limit comparison test, which says you have two sequences, and as long as they have the same growth, in other words, they go to 0 at the same rate of speed, then they both have the same behavior when it comes to converging and diverging. And so there's these three possibilities, but focus on the middle one. This middle one is the one you want. It's the get rid of the noise. And it says the following. If you have terms with pluses and minuses, get rid of them. How do we get rid of them? We say, which thing grows faster? And we only keep the fastest growing parts. We keep the fastest growing parts upstairs. We keep the fastest growing parts downstairs. So there's no more plus or minus. We got rid of the noise. And once you do that, your new series will be much simpler to determine whether it converges or diverges. And then we can say, well, what's happening with our original series? Now, when it comes to saying, well, what grows the fastest? You should understand how things relate. Constants, down here in this lower corner, constants are much less, they grow slower than everything because they don't grow at all. Logs are a little bit faster than constants. They grow very slowly. Polynomial, n to a power, n to a number like n cubed, n to the fifth, n to the thousandth, it grows faster than anything that looks like a log. Exponential, something, a number to the n, that grows faster than anything polynomial. And then factorial can beat exponential. Now, is this everything? No. But these are the common things. So it's good to have a sense of like, what's going to win in the race? That helps you understand the speed of things. And in some sense, you can get to the point where you can say, I know the answer before I even begin. Then the work is to justify the answer. So that's what we want to be able to do. I know the answer before we begin. Ratio and root test, both have the same flavor. They say, if I were a geometric series, which geometric series would I be? So you're after some multiplying factor, which we call rho. In the ratio test, you take the ratio of the next term over the current term. In the root test, you take the nth root of the nth term. If you get something less than 1, it converges, and it converges in a very strong sense. It's always absolutely converging. If you're bigger than 1, it diverges. If you want to call it absolutely diverging, you can. But essentially, if you're bigger than 1, you fail the nth term test. And if you're equal to 1, more work. Lots of these things involve limits. There's a limit, 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 limit. So you should know some basic limits. You might need to use L'Hopital. 2 limits that show up as n goes to infinity of n to the 1 over n, that's 1. As n goes to infinity, 1 plus t over n to the nth power, that's e to the t. And these show up particularly in the ratio and the root test. And you might wonder, why am I very excited about the ratio test? Well, that's not to say I'm excited about the ratio test. What does this indicate? Factorial. Ah, yes. Okay. So the last 2 things, there are 2 types of series that we understand very well. Geometric. If we're geometric, we converge as long as our multiplying term, r, is less than 1 in absolute value. Then the other one is p-series. And oops, I have a small typo here. This should be r to the n. Sorry about that. So r to the n converges if and only if r is small. 1 over n to the p converges if and only if p is greater than 1. What's on this slide? I know there's a lot. This is what you use to answer questions about converging and diverging. It's all there. Do you have any questions? Okay, good. So then we're ready for anything that we might encounter. So today is review day, but I want to think of it as practice day. So I grabbed some problems from old exams, and they tend to look like this. So you have a series, and now the question is, does this converge absolutely, conditionally, or does it diverge? Now, these are on the back of your handout, if you don't like to read from a distance. And what we're going to do is we have 4 rounds. So I'll give you a couple of minutes to work on it. Then we'll come back together, and we'll talk about which ones they are. Don't worry about the justifying right now, or just make it very simple justification. Your goal is to say, does this converge absolutely? Does it converge conditionally? Does it diverge? Can you recognize that? And you can talk to your neighbor. That's great. Practice. You don't have to go in order. If you see one, like say, I know what's happening to that one, jump to that one, and then come back and do the other ones. So, all right. We'll work on these for a couple of minutes, say 5 minutes or so, and then we'll come back together and we'll talk about the answers. All right, so let's see. The first sum, -1 to the n over n plus 2. What can we say about it? What? Anybody can throw out a guess? Conditional. Conditional is correct. It converges because alternating series in terms go to 0. If you drop the alternating, it looks like harmonic, which diverges. Okay. The next one, cosine n pi over n squared. Absolute, conditional, or divergent? Absolute. It is indeed absolute. Now, the cosine n pi is a plus minus 1. But just because it's plus minus 1 does not mean it's conditional. You say, well, hey, what if I drop the plus minus 1? It looks like a p-series with p equals 2. Okay, 3 plus n plus 2n squared over 5 plus n plus 3n squared. Absolute. Absolute, conditional, or divergent? Absolute. Divergent. Okay, why is it divergent? What happens if you ignore the sum, look at the term as you go to infinity? What do you get? You get 2 over 3. It's the nth term test. The terms don't go to 0. Okay, sum -1 to the n to the 10th over 10 to the n. Absolute, conditional, or divergent?
Absolute.
It's absolute. Now, what happens? Take the root test, because you see things to powers. But really, what do you have upstairs? Let's just say what we have upstairs. Polynomial. What do you have downstairs? Exponential. Who wins the race? Exponential wins, and it's a lot bigger. So this should be something that we expect converges. If you take the root test, you get rho equals 1/10. And that's less than 1. All right, last one. The sum of the square root of n plus 1 over n cubed plus 2n. Absolute, conditional, are divergent. Why can't it be conditional, by the way? What does this not have? There's no plus or minus action going on. If there's no plus minus action going on, conditional is off the menu. It can't be conditional, because the absolute doesn't do anything. So does this converge or does it diverge? It diverges. Why? Well, throw out the lower order terms. You look like 1 over n. 1 over n is harmonic. That diverges.
Real quick, I don't believe it's too silly. I mean, n plus 1, does it get negated by the square root? Or?
Nope. This, focus on the growth. Take the highest growing terms. That's what you need to look at. All right, how'd you do? That's just your warm-up round. Don't worry, we have more rounds to go. All right, we're ready now for round 2. Same thing. Talk to your neighbors. We'll just start at the top. The sum of -1 to the n cosine 1 over n squared. Absolute, conditional, or divergent? Anyone can answer. Diverges. Because the terms don't go to 0. It's the nth term test. Cosine 1 over n squared is going to 1. Yes? No? All right. The next one. Log of square root of n plus 1 minus log square root of n. Absolute, conditional, or divergent? Divergent. Because this behaves, if you use properties of logs, it's a lot like log of 1 plus 1 over n. Log of 1 plus small thing is approximately small thing. So it behaves like 1 over n. 1 over n is harmonic, it's divergent. This one's tough. This one's right on the edge of not working. All right, -1 to the n over the square root of n squared plus 1. Absolute, conditional, or divergent? It is conditional. Alternating terms go to 0, so it converges, but if you drop the -1 to the n, it looks like 1 over n. You can do a limit comparison test, get rid of that plus 1 downstairs. Square root of n squared is n. Okay, 3 to the n plus 4 to the 2n divided by 2 to the n plus 5 to the n. Absolute, conditional, or divergent? Can't be conditional, there's no plus minus 1. So it's either absolute or divergent. It's divergent. Why is it divergent? What's another way to say 4 to the 2n? 4 to the 2n is also known as 16 to the power n. Like it's 4 squared to the n. The upstairs looks like 16 to the n. The downstairs looks like 5 to the n. These terms are blowing up. Nth term test doesn't go to 0. All right, n factorial divided by n to the n. Absolute, conditional, or divergent? Absolute, conditional, or divergent?
Divergent.
Absolute.
God damn it.
Now, if you apply the ratio test, and why would we apply the ratio test on this one? Factorial. If you apply the ratio test and work it out, it approaches 1 over e. Now you might say, well, wait a second, Steve, you said factorial, that was the big one. Yes, but there's always a bigger fish. N to the n beats factorial. They might say, well, wait, isn't n to the n polynomial? No, polynomial is like n to the 5th. Or you might say, hey, isn't n to the n like an exponential? No, exponential is like 5 to the n. When you mix both n upstairs and downstairs, it's a different animal altogether. All right, how'd you do? It's okay, we're going quickly, and you haven't had practice. That's why we're doing this. You'll get better, because we're going to do it again. All right, here's the next block. We'll start at the top. The sum, seems like there's a lot of noise here, 3 root n plus 4 over 5n squared minus 6n plus 1. Is it absolute, conditional, or divergent? Absolute. What's the right test? Limit comparison test. Get rid of that noise. This behaves like 1 over n to the 1.5. Bad handwriting, but. All right, the next one. 3 to the 2n divided by 4 to the n plus 2 to the 3n. Absolute, conditional, or divergent? Divergent. Because the upstairs is like 9 to the n. The downstairs is like 8 to the n. It's blowing up to infinity. So nth term test rules it out. Sine of 4n cubed plus 7 divided by n to the 4th plus 7n. Absolute, conditional, or divergent?
Conditional. Absolute.
Absolute. Now, regardless of what's on the inside, you have a sine. Sine can't be very big. It's at most 1. So this looks like essentially 1 over n to the 4th. And 1 over n to the 4th, that's a p-series, which converges. Sine pi n times root n. Absolute, conditional, or divergent? Absolute. Why is it absolute? That square root of n gets big. Sine of pi n is always 0. So you're adding up 0. And it turns out adding up 0 is easy to do. All right, last one. Negative 1 to the n, alternating. Okay, so this one has a good chance to be conditional. Root n minus 1. Absolute, conditional, or divergent?
That is conditional.
Divergent. What's happening? Think about the denominator. Root n and root n minus 1 are very close to each other. So this is almost 0 downstairs, which means you have a big number. The terms aren't going to 0. They're getting arbitrarily large. You can make it more rigorous if you multiply by the conjugate. So essentially, this is behaving like 2 root n. So even though it's alternating, the terms don't go to 0, so it's divergent. Now you might notice none of them were conditional. We never made a claim that they had to be. And there was an exam a few years ago where it was very similar to this, where we put them all as absolute or divergent. And one student was like, well, I'm just going to get some points. I'll circle the middle column. Did not go well for that student. So don't just randomly guess. Guess in a smart way. Our last block. The first one, negative 9 to the n divided by 3 to the 2n log n. Absolute, conditional, or divergent?
Absolute.
Conditional. The 9 to the n and the 3 to the 2n do what? They cancel. So it looks like negative 1 to the n over log n. It's alternating going to 0, so it converges, but 1 over log n diverges. Okay, the next one, a bunch of mess. Absolute, conditional, or divergent? Divergent. The mess that you keep is the 4n squared over n cubed. That looks like 1 over n. So that's harmonic. Okay, next one. N plus 2 over n cubed minus 2 plus 10 to the n over 5 to the 3n. Absolute, conditional are divergent. It's absolute. Both pieces are behaving nicely. This looks like a p-series, 1 over n squared, and the other one looks like a geometric, which has a term smaller than 1. Cosine 2n over n factorial. Absolute, conditional are divergent. Absolute. The top is bounded by 1. 1 over n factorial. That goes to 0 super fast. You can do like a ratio test. You get rho equals 0. Sum 2 to infinity, negative 1 to the n plus 1 over n factorial log n. Absolute, conditional are divergent. Divergent. N factorial trounces log n. This blows up super fast. All right, so this was our practice. We continue next time on our road to Taylor series.